I'm pretty sure you guys have seen this kind of limits in your Calculus 1 class, and they look super scary. But don't worry, because I will give you guys 4 examples like this to make it super clear for you guys. This is an example of a limit of a Riemann sum, meaning that this right here actually represents the area of a region. So if we can find out what that region is, then we can just integrate it and then get the answer. So that will be the strategy. Let's do a quick review right here. Suppose we have a function, let's say like this, y equals f of x. And let's say we want the area going from A to B. Okay, so how do we do it? The idea is that we are going to use n equal width rectangles. Technically, non-equal width is okay, but to keep things simple, we use equal width rectangles. So let me just draw a rectangle like this right here. And it doesn't matter if you put the left endpoint or the right endpoint. Here, I'm using a right endpoint rectangle because the right endpoint here touches the curve. There are a few things that we have to know. The first thing is that this right here is the width of the rectangle. It's denoted by delta x. Next, this right here, because we're using the right endpoint, so we're looking at this x value, we are going to denote that by xi. And maybe you guys notice my shirt that has the xi star. The star means that when we are not using the equal width rectangles. And that's technically the definition of integral. But this right here, of course, works out much nicer with equal widths. So let's see, when we have xi, we can just plug it into the function so we can get the vertical distance, the y value, which will be the height of the rectangle. That will be perfect. So we will just get f of xi. Now, we have this rectangle. What's the area of it? Base times height. So here we will have, let's put down f of xi like so, and then multiply by delta x. All right, so this is just one rectangle. It's not enough. How many did we say we have? N of them. So we are going to be adding them up. So we will have the summation, and the I is the index, will be going from 1 to n. So we have n of them. But you see that we have all the parts are sticking out, right? We don't get the area under the curve. Don't worry, because now we'll take the limit as n goes to infinity, because when n goes to infinity, the rectangles are super thin. So you actually fill in the whole thing. That's the definition of the area for that. All right. Now, a quick question for you guys. How are we going to find the delta x? Well, we are going from A to B. So the interval, it has the length b minus a. So let me just write it down right here. Delta x will be equal to b minus a. And then we are dividing into n equal width rectangles. So just divide it by n. All right. So that's the structure of this kind of limits. Notice b minus a over n. Aha, you see that everybody has that 1 over n. So that's the hint. B minus a is equal to 1, meaning that the width of the interval that we're talking about has length 1. All right. And then we see that we have the input square, and all that. That's the f of xi. So we know the function is x squared. Okay, so let me just draw a picture specifically for this limit for you guys. In fact, this right here represents, well, the width is 1, right? From 0 to 1. And then the reason it's from 0 to 1 is because we're just talking about x squared. Yeah. It could have been from like 2 to 3 because that interval also has length 1. But I will show you guys the example later on. But here, I will convince you guys by giving you guys a picture. Let's say this right here is y equals x squared, and we are going from 0 to 1. So let's talk about what this represents. Firstly, we have 1 over n, so that will be the width of the first rectangle, and denoted by 1 over n. And very conveniently, we can just put 1 over n into the function x squared, and we can actually get the height. So go up, hit the curve, and then make the rectangle. So this rectangle right here has this area. Next, well, because the width is 1 over n, so that means when we move to the next rectangle, this right here, the x value is 2 over n. Starting from here, go up, and then make a rectangle like this. the width right here is still 1 over n, but the height is we use this x value and we put it into the function, so 2 over n squared, and then so on, so on, so on. And then lastly, we can do this. This is 1, but we can purposely write it as n over n, go up, hit the curve, and then make a rectangle like so. The width is 1 over n, the height is n over n squared. All right? So this is the region that we're talking about from 0 to 1 under x squared. Well, convert this into into an integral, it will be just the integral sign. By the way, have a look. This is the summation sign. In Greek, this is a sigma, s, right? This is actually also an s. It's like a super version of an s. The limit of a sigma becomes the summation. And then we are going from 0 to 1, right? And then the function that we're talking about is x squared. And as you can see, earlier here we have the function, right? F of xi, but right now we can just put down the function that we're talking about. And then, of course, you see that earlier we used delta x for the width of the rectangle. Right now, we are going to be using dx. So, this notation has a meaning. This is like the width of each rectangle, right? And then this is like the height of each rectangle. And then the integral sign means that we are going to add up all the rectangles from 0 to 1, okay? And then to do this, thanks to the Fundamental Theorem of Calculus Part 2, we can just use the reverse power rule, so we can find an antiderivative. So add 1 to the power divided by the new power, we get the 1/3, and then we will get 1/3 x to the third power, and then we will just have to plug in numbers, putting 1 first and then putting 0. Ladies and gentlemen, we will get 1 over 3 times 1 to the third power. That's the first part, and then minus 1 over 3 times 0 to the third power. That's 0. Work that out. We just get 1/3. So this scary limit has the answer 1/3. Okay, second question, and this right here is actually similar to the first one. And with this example, I can show you guys why we do not have to start with 0 all the time. Have a look. First, we should notice that everybody has 3 over n, so that will be the delta x. And then the number on the top, it will be the b minus a. So let's go ahead and make a quick note. B minus a is equal to 3, and it means that our length for the interval has 3. So it could be like from 0 to 3, or from 1 to 4, or from 17 to 20, right? Based on that, we don't know yet. Now, let's look at the function part. So we can see that we have this as the input to the second power, okay? But we have to pick up what exactly is changing. So the 2 stays for all of them, okay? And then everybody has that n on the bottom, okay? But we see this is 3, 6, 9, and then 3n. So where's the 1, 2, 3, 4, right? Well, this is the time that we have to actually break it apart ourselves. 3, it's the same as 3 times 1. 6, it's the same as 3 times 2. And then 9, it's the same as 3 times 3. And then so on, so on, so on. And lastly, we see that this right here is, of course, the same as 3 times n. So the red numbers that I put down earlier, that would be the I. So if you would like, you can go ahead and write that as a summation. And perhaps I'll do that for you guys real quick. Because this question could also have been written like this. The limit as n goes to infinity. And then perhaps they will factor out the 3 over n and then put it all the way at the front, like right here. Not really at the front. It has to be after the limit. Right? So put it down right here first. And then the summation. And then we have the I going from 1 to n. And then we'll just put on the rest. We have the 2 plus. And then notice that everybody still have that 3. So we have to put on the 3. And then 1, 2, 3, 4, and up to n. That will be the I, because that's the running index. And then divided by n. And then square. So this right here will be a more compact form to ask the same exact question. Alright, so and this right here fits more like the definition of the integral. Alright, so the best way for me to explain this is, of course, to give you guys pictures. I think this right here will still be more clear, but just be really careful. if the question is asking you like this, which we'll do next for the next example. So I'm going to claim that because we know b minus a is equal to 3, so we can just go from 0 to 3. And this right here will give you the function. But what exactly is the function though? We see the 2 right here plus, okay, 3i over n. So is it just x and then square? Or is the function 2 plus, maybe the 3 has to be in the front because earlier we had that I over n, right? So maybe it says 3x and then square. Or is it just x squared? Which one? The answer is this one. We pay attention to the 3i over n because we have that 3, so you have to put the 3i together. Okay, so here's the picture for you guys. And we have 2 plus x to the second power, so we'll move the parabola twice to the left. So let's say this right here is -2, and then we have that parabola like so. And I'm just going to put down y is equal to 2 plus x and then square. And then we are going to go from 0 to 3. So somewhat like this. Okay, now keep this in mind. Right here, we are going to integrate from 0 to 3, find this area. So each width will be 3 over n. So I'm just going to make a cut. This is 3 over n. And you see, we are using this as an x value. We can just go up and then hit the curve and then draw our rectangle. So as we can see, the first rectangle has the width 3 over n times, we put the 3 over n into this x, and we get 2 plus 3 over n squared. The next one, of course, each time we will have to go up by 3 over n. So the next one will be 6 over n. And notice that the width is still 3 over n, but we are using this for the x value. Put it here, we go up, and then we see that the height of this rectangle will be 2 plus 6 over n and then square. So this right here is the function. And then of course now we can just integrate this from 0 to 3. And then here we have the function 2 plus x square dx. Okay. And I'm going to leave that to you guys to integrate. So maybe you guys can integrate that and then put down the answer down below, because I want to focus on how to get a setup for it. All right. So now, why is it always from 0 to 3? As I told you guys, it does not have to be. So now I'm going to claim the following. I'm going to give you guys another picture. And this time though, my function will just be x squared. And I'll tell you that this right here will also work. So this right here is just y equals x squared. But if we are talking about just x squared, then we will have to integrate it from 2 to 5. Why 2? Because as you can see, everybody has that 2 inside. All right, and then why 5? Because remember, this length right here has to be 3 because b minus a has to be 3. If we study at 2, we'll just go up to 5. And as you can see, this region, it's the same as that region because we just take this picture and then move it twice to the right. Okay? So that's how it works. But I will just talk about this real quick. Suppose you have this region and you want to set it up. Then this is how you do it. Firstly, the length right here is 3. Divide into n pieces, so each one will have 3 over n. But the first x value will be what? This is not just 3 over n anymore. This right here is, we have 2, and then we have to add it with 3 over n. Right? Because this much is 2 already, this much is 3 over n, so from here to here is 2 plus 3 over n. So as you can see, this right here, for the first rectangle, it has the width 3 over n, but the height is, we have to use this x value, and then we put that into this function, and then you see we should go up, and then we can make a rectangle like so. And the height is this, which is 2 plus 3 over n, and then square. Let's do another one. The next one will be what? We have to add another 3 over n, so double of the 3 will be 6, and then divided by the n. But don't forget, this x value will be 2 plus 6 over n. So same thing. The width right here is 3 over n, and then we can just multiply this with, put this right here, so we get 2 plus 6 over n, and then square, and so on, so on, so on. So in fact, you see, this right here are the same, and we can also go ahead and just do the following. The integral going from 2 to 5. And then what? Just x squared dx. Alright? So of course, you can see which one's easier for you to integrate, and the blue one will be easier to integrate. And in fact, if you do the so-called U substitution, you can go from here to here. And if you want to have some fun, you can try to think about how to change this so that you can go from 17 to 20, but I'm going to leave that to you. By the way, please go ahead, work this out on your own, and leave the answer in the comment section along with the timestamp. Alright, for the third example, I'm just going to give you guys like this. So the deal is that how can we convert this into an area question, right? So here's the deal. We have pi over n, so that's the delta x. Here we have pi, so that means we can just go from 0 to pi, right? If you want, you can go from pi to 2 pi, but we talked about it earlier already. And here, seriously, just go from 0 to pi because we have sine, and what's the function? Just x. And the reason that it's just x, it's not like 2x or 5x, it's because we have the pi I, okay, pi I. If there's a 2, then I would say the function is sine of 2x. But in fact here, I'm just going to again draw you guys a picture to convince you guys why this has to be the case. We are talking about the sine function, so I'm just going to draw a picture like this. So this is the classic sine curve. So we are going to go from 0 to pi, cool, and then divide this into n pieces. So each piece will have the width pi over n. And you see, the width right here is pi over n, and then we can just go up and then make a curve. I mean, not make a curve, make a rectangle. Yeah, so the first one is put the pi over n into the sign. So we have pi times 1 over n, right? Because remember, the first one is when I is equal to 1. Next, we will have 2 pi over n, because you just double that. And that will be the x value. You go up, and then you can make a happy rectangle like this. We will still have pi over n, and you see it's 2 pi over n because I will be 2. Put it here, and so on. Yeah. So that should be pretty clear. This right here, we can just convert that into the integral going from 0 to pi, and then we have sine x dx. I'll work out this one for you guys because I know you guys worked so hard on that integral I gave you guys earlier. So I'll do this for you guys. To integrate sine x, we will have to be thinking about the derivative of what will give us sine x. Not just cosine, but negative cosine. Right? So this right here gives us negative cosine x. Because the derivative of cosine x is negative, sine x, negative times this negative gives you the positive. Okay, and then we can now just go from 0 to pi, put it in. So first, we get negative cosine pi, that's the first part, minus, this time 0 matters. Be really careful, we have negative cosine 0. Why 0 matters? Well, this right here is 1. Cosine 0 is 1. So be really careful. When you see 0, please don't ignore it. Plug in and actually work that out. Okay, here we have cosine pi, which is negative 1. Negative 1 times that is positive 1 altogether. So perhaps I'll just write this down right here. This right here is negative 1. So just be super careful with all the trig functions, values, all that stuff. So ladies and gentlemen, negative 1 is 1. Negative times negative is plus. This is just 1 plus 1. The answer is 2. So cool. Why is that? Because the whole area here, it's like a crazy shape. But the area is so nice, it's just equal to 2. Alright, last example. We have the limit as n goes to infinity of 1 over n times the summation I goes from 1 to n, and then we have n squared over n squared plus I squared. Wow. Where is the I over n, that kind of thing? Well, this is just I squared, huh? This is what we have to do. We really want to see the I over n because that would be the input. Okay, here we have n squared, and this is also I squared. Let's divide everybody by n squared. That's the strategy for this one. Divide this by n squared, divide this by n squared, divide this by n squared. So we can rewrite this as the limit as n goes to infinity. We still have that 1 over n, and then we have the summation. I goes from 1 to n. And then on the top, we just have 1. On the bottom, this is 1. And then this right here, put a parentheses, and then we will have I over n, and then square. Yeah. Very cool, huh? Okay, what's the function? 1 over 1 plus x squared. Going from where to where? 0 to 1. Because right here, this is just 1 over n. Cool, huh? So, this right here, perhaps I'm just going to give you guys the integral. It's just going from 0 to 1. And then we have to integrate 1 over 1 plus x squared. So, now the question is, what's the derivative? Sorry. The derivative of what function will give you 1 over 1 plus x squared? Natural? No, just kidding. Inverse tangent. This right here is inverse tangent of x. And then we'll just have to go from 0 to 1. So this right here is inverse tangent. Put the 1 in first. So that's the first part. Minus, put a 0. We have inverse tangent of 0. Okay, remember your inverse trig functions as well. Inverse tangent of 0, this is 0, because tangent of 0 is 0. And inverse tangent of 1 is pi over 4, because the regular tangent of pi over 4 will give you 1. So all in all, this right here will give us pi over 4. Right? So that's that. So hopefully my examples have helped you, and the best way. So hopefully my examples have helped you, and right now I want you to get. So hopefully my examples have helped you, and right now I want you guys to go ahead and try these 3 questions. Convert them into integrals and then work them out, and comment your answers in the comment down below. Alright? So yeah, go ahead and really do it. By the way, there's no typo. I meant to put a 1 here, and then this right here is a 2, and then the I.